In today's lecture, we will study about message authentication and entity authentication. First, we will discuss what is message authentication, and then we will study about entity authentication. Message authentication is a mechanism to verify the received message that has come from an alleged source or sender, and this message has not been altered. The alteration is taken in terms of contents, sequencing, means sequence number of the transmitted packet, and timelining. These are the three things that we consider while we see the message, whether the message has been altered or not. So message authentication is a mechanism that verifies that the received message has come from the alleged sender, which means that the source from which we are expecting the message and it has not been altered. Thus, it provides protection against masquerading, content modification, insertion, deletion, reordering of the message, and delay and replay of the messages. These are the following things for which message authentication provides protection. There are two levels of functionality in message authentication. First, we produce a value that is used to authenticate a message, and that value is called as authenticator. And then we use this authenticator in some higher level protocol. Maybe we can use it at application layer in the OSI model that enables the receiver to verify the authenticity of the message. And this authenticator can be produced by using any one of the following ways, and the ways are message encryption that we already have studied. The other way is message authentication code. We will study this also. And the third way of producing the authenticator is the hash function. So all these three factors, they are responsible to produce the authenticator. Now, what is authenticator? Authenticator is basically a kind of value that we can use to authenticate message. Message, I mean to say, is our plain text. Now, we will see one by one these ways by which we can produce the authenticator, the value that is required to authenticate the message. So, first we will start with the message encryption process. Message encryption can provide a measure of authentication. We have already seen that in the symmetric or asymmetric encryption, we can encrypt the message, and that ensures the authentication of that message when it is in the encrypted form. And for that process, we can use both symmetric and public key encryption schemes. In symmetric encryption, since the shared key that is known to the two parties is used, we have studied about symmetric encryption, and in symmetric encryption, we have a shared key, and this shared key is known to the both the parties who are communicating. So the receiver is assured that the message has come from the alleged sender, that the message has come from the some legitimate source. So it is ensured that the message has come from some legitimate source while we use this symmetric encryption, where we use one single shared key. But as we see that message encryption is done and authentication is achieved, but there should be some automatic way to determine whether the ciphertext which we obtained by the symmetric encryption belongs to some legitimate message. So one solution to this is to force the plain text to have some structure. For example, we have a frame check sequence. Frame check sequence, or simply it is checksum. This checksum can be appended to each message, and at the destination, a checksum is again computed and compared with the received checksum. Okay, and then we see whether the both the checksum, one is which is transmitted with the message and the other which is computed at the destination side, are they equal or not, and then we can decide whether this message is authentic or not. So we have when we use single key, for encryption, we have the following structure. We have message that we want to transmit, and this message is given to some encryption algorithm. And since it is a symmetric encryption, then we apply here the single shared key, and then we get the message in the encrypted form. Suppose this is the message after encryption. So here we have obtained this by applying the encryption algorithm, then the key and message, and we get this encrypted message, and then it is transmitted. And at the destination side, we use a decryption algorithm, and we apply the same key that we had used at the sender side, and then what we are going to get, we are going to get message. That is a simple encryption model that we have studied for the symmetric encryption. Now for another model that where we can use the private key, and that private key, when we use for the encryption, that provides the authenticity of the message. In this particular scenario, this first scenario where we are using the symmetric encryption, and here we are getting the confidentiality. And when we take the message, and we apply some encryption algorithm to this message, and here we apply the private key of the user. This is the private key of the user, and then we get the message in the encrypted form like this. So it is a function of this encryption algorithm: key, the private key, and the message. And then we transmit this message, and at the destination side you apply some decryption algorithm, and here you apply not the private key but the public key of the same user, and then you are going to get the original plain text or the message. Fine. So this is the scenario where we are using asymmetric encryption. The first scenario is providing us confidentiality, and the second scenario is providing us authenticity. You can also say that we are getting authenticity here as well, as we are encrypting this message. There are two ways of computing the checksum. As I just told that there must be some automatic way by which we can prove the authenticity of the message, that is the origin of the message, that it has come from some legitimate source. So for that we have to compute the checksum. Okay, and there are two ways by which we can compute the checksum. First way is computing checksum first, followed by the encryption. So in first way, first we compute checksum and then we do the encryption. And the other way is to do the encryption of the message first, and then it is followed by the checksum computation. So first we do the encryption and then we go for the computation of the checksum. So these two processes are different. I will draw the structures and you will come to know the difference between these two ways. For the first case, you have a message to encrypt, and to this message you apply some function f, and then the output of this function is concatenated with the original message. And after concatenation, what you are going to get, you are going to get message, and with this message you are appending the checksum that you have calculated by using this function f. So here you have the original message, and this is the checksum part that you have calculated by using the function f. And after that you will provide the encryption algorithm or the encryption function, and to this encryption function you are providing the key, and then you are getting the complete message along with the appended checksum in the encrypted form. So this is going to be your encrypted message, and here it is a function of this encryption algorithm the key applied, and the message content here is the original message that is concatenated with function of m, that is your calculated checksum. Fine. And then you are going to transmit it towards the destination side, and at destination you are going to use the decryption algorithm, and you will apply the same key k, and after decryption you are going to get the original message m that is appended with the checksum, that is your function of message that you had calculated using the function f. And then you apply here on the original message the same function that you had used for calculating the checksum, and you again calculate checksum at destination side, and then you take this already calculated checksum which was appended to your message, and what you do here, you compare both these checksums. So you compare both these checksums. If these both these checksums, if they are same, then your message is authentic. If there is some difference, then you cannot say that your message is authentic. So this is the approach, that is the first approach, where you are computing checksum first, and then you are performing encryption after that. Okay. In the second approach, first you are performing encryption, and then you are computing the checksum. So for second approach, the structure is like this. First you have message, and then you will apply the encryption function. Some key will be applied to this, and you are going to get the message in the encrypted form. So suppose this represents your message in the encrypted form, and then you are applying the function f that is used to compute the checksum, and the output of this function and this encrypted message, they are concatenated. And after that, in the next step, what we are going to get after concatenation, the encrypted message and its checksum that is appended to this encrypted message. And this checksum is basically a function of encryption function that is done with the key on the original message. So this is what this is appended to the original message, and then what we do, send it we send it towards the destination side, and at destination side we are using the decryption algorithm, we are applying the same key, and then we are going to get original message after decryption. And along with this, we are fetching this encrypted part to this place. We are applying here the function that will calculate the checksum here again, and there will be some output, that is the checksum that we will compute here on the destination side. And along with this part, that is the calculated checksum at the sender side, and this is brought to this point, and at this point both these checksums are compared. Checksums are compared. If they are same, then your message is authentic, then your message has come from the alleged source, some legitimate source. If they are different, then it is not coming from some authentic source. So these are the two ways. First way, where we compute first we compute the checksum, and then we do the encryption. In the second way, first we do the encryption and then we compute the checksum. So it is clear from these two structures, the second approach is not preferable, as the opponent can construct the message with varied checksum even without knowing the original message. So this confusion and disrupt operation at the receiving end. So this will create some confusion, and it will disrupt the operation at the receiver side. In fact, any sort of structuring added to the transmitted message serves to strengthen the authentication capability, for example, header checksum. So we do not prefer the second approach. Only this first approach is preferred, because first we are computing checksum here, then we are appending it to the message, and after that we are doing the encryption here, and then whole message is transmitted or sent to the destination side. And here at the destination side, this is happening. First we do the decryption, then we get the message that is appended with the checksum, and then we again compute the checksum from the message received, and then we compare both these checksums. If they are same, then the message is authentic. So that is the way how we calculate checksum and how we can authenticate the message. Okay, so this is all what we do by using the message encryption process. How we can produce the checksum value, that is what we call as authenticator. So that authenticator is used to authenticate the message, and whole this process happens in the encryption process. Then we have another way of producing the authenticator, and that is MAC, message authentication code. Message authentication code is a small block of data, and this small block of data is a function of message and key. So here we use message and we apply some key. So it is similar to some cryptographic function. So this is going to be a cryptographic checksum. So here, even without using the encryption algorithm, we are computing the checksum, but here we are applying the key to the function which is used for calculating the checksum, and that's why it is called as the cryptographic checksum. And alternatively, this MAC is also known as MIC. That is message integrity code. This MAC is appended to the message and then it is transmitted towards the destination side. And this MAC can be computed in two ways. First way is MAC computation over plain text followed by encryption, like we did in the previous case. And then the other case is message encryption followed by the MAC computation. So in this case, first we compute the MAC, and then in this case, first we do the encryption and then we compute the MAC. So it is similar to the previous process. And at destination, MAC is again computed and compared with the received MAC. If two MACs are similar, then there are different cases. The case number one is receiver is assured that message has not been altered. So if both the MACs at the receiver side, if they match with each other, then the receiver is assured the message has not been altered, because altering message without altering MAC will not make the two MACs equal. So that's the reason why the receiver is assured when two MACs are equal. Then a receiver is also assured that message is from the alleged sender, which means that the sender from which message was expected. And this is because no one knows the keys and none else could have computed the proper MAC. Because when there are two communicating parties, okay, for example, we have communication party 1, communicating party 2, and when they want to communicate, there will be a key K here and the same key will be here. So receiver is assured that the message is from the expected sender in the network, because no one else would know about this key, and this key will be along with the alleged senders or the legitimate senders which want to communicate. And the third one is if the message contains a sequence number. If you have the sequence number in the message, then the receiver is assured of proper sequencing, which means that there is no alteration of the message, or there is no drop of message has occurred. And the sequence number, like we have the sequence numbers in the TCP, and we have in the HDLC, we have sequence number in the X25 protocols. So we have sequence numbers. If there is presence of sequence numbers in the packets, then the receiver is assured that there is a proper sequence. That means there is no drop of the packet has occurred. Message authentication without privacy. So message authentication code without privacy. So I will draw a structure for that here. We are not using privacy here, but we are computing the MAC here. Initially we have a message M that we want to transmit, and will be this message M will be given to a function, and here the function is represented with this letter C, and to this function a key K is applied, and the output of this function is concatenated with the original message, and the output of this message is a function of C encryption using key K over this plain text M, and this is similar to the encryption function. And after that, what we are going to do, we are going to send this message towards the destination side, and this message is sent in the form of original message. This is the original message, and it is appended with the MAC that we have just calculated. So this part is going to be MAC. This is your MAC part, message authentication code, or the message integrity code. And then at the receiver side, this is sent, and here again the same function C is applied to the message, same key K is applied, and we get the checksum, or here we call it as MAC. Okay, this is what we are going to compute MAC. And the other MAC that is appended to the message, it is fetched to this point, and here both these MACs, they are compared. Again the condition is same for this. If these two MACs are same, then the message is authentic, there is no alteration of the message. If they differ, then there is the alteration of the message. So mathematically we can write MAC as C, that is your function to calculate MAC using key K over message M, and where C is similar to your encryption function. And like encryption function, this C need not to be reversible. C need not to be reversible, which means that it is a one-way function. Now, since we see that symmetric encryption will provide authenticated authentication, and then why to have a separate MAC when we are having authentication that is provided by symmetric encryption or asymmetric encryption? Then why we go for the MAC computation? And there are some reasons for that. So why MAC when symmetric encryption provides authentication? There are some reasons, and the first reason is same message is broadcasted to a number of stations. When we have number of stations, we have to transmit the same message, and the message may be sent in clear with a MAC appended to it. For example, a notification, when we have to send a notification. For example, in a university system, we send a notification to number of stations or number of users, and the notification may tell regarding the unavailability of network to the users. That's an example. And in it is then cheaper or more reliable to have only one destination responsible for monitoring authenticity of the message. So there will be one station that will monitor the authenticity of this message, which will compute the MAC and which will compare the MAC. Okay, so for that purpose, where we have to broadcast a message for number of users, where we do not need encryption, then we use this MAC to authenticate the message. Another reason to use MAC is heavy load scenario. In heavy load scenario, where the receiver cannot afford to decrypt all message, when we have lot of messages coming, and we cannot afford to decrypt all the messages, so authentication then carried on a selective basis and at random fashion, can be useful. So this can be done by using Mac. So when we have a lot of messages are being received, and in such scenarios we cannot afford to decrypt all the messages, so there we prefer this Mac. It is used to authenticate messages. And after that, we have the other reason, that is wait a minute. Okay, the third reason is authentication of a computer program sent in plain text. Sometimes we send a computer program in the plain text, so program can be executed without decrypting it every time, which would be a wasteful. If we first decrypt a program and then we execute that program, that is going to waste the resources of our processor. So instead of doing that, if we have appended Mac to the program, then we know that this is an authentic message, and we can prove the authenticity by calculating the Mac, and then we go on direct executing the program. So in that way we we uh, we save our resources of our processor. So that is another uh, reason why we use Mac instead of encryption. Then fourth reason is we use this Mac calculations in applications where message secrecy is not of importance, and but the authenticity of the message is important. So there are some applications where we do not require privacy, we do not require security, but authentication is of importance. For example, we have simple network management protocol, SNMP protocol, which separates functions of confidentiality and authenticity. So in such scenarios where we do not require confidentiality or the privacy of the message, there we use this Mac codes. The next reason why we need Mac instead of encryption is that there are certain functions which are separating authentication and confidentiality, which afford the architectural flexibility. Because of separating these two terms, authentication and confidentiality, there is a way out to our architectural flexibility. For example, it may be desired to perform authentication at application level, but to provide confidentiality at lower level, such as we can provide confidentiality at transport layer, and this authentication may be at application layer. So in these cases, when we require authentication at application layer, we will go for this Mac at authentication. We will not do the encryption there. But here, when we are at transport layer, we can go for the confidentiality at that place. And the next reason why we require Mac is for prolonged protection. Now, what is this prolonged protection? Sometimes a user may wish to prolong the period of protection beyond the time of reception of message and yet allow processing of message contents, because sometimes user want to keep the message protected beyond the usage of that message contents. When we go for message encryption, the protection is lost when the message is decrypted. So the message is protected against the fraudulent modifications only in transit but not within the target system. So when we keep the message in the target system and we want to keep this message beyond the usage of the message, then we use Mac there, so that no alteration should be done in that place also. So these are the reasons why we prefer Mac in some applications instead of going for the encryption process, although symmetric encryption is also providing us the authenticity of the message also. Next we have hash function that can be used to provide the authenticator, which we can use to authenticate the message. And a hash function is basically a function that maps a message of any length to a fixed length. The message can be of any length, and we get a hash that has a fixed length, and this is denoted by h of m. and this hash value is also referred as MD, that is your message digest. And this message digest is calculated from the message itself, and the message can be of any length, but this message digest is going to be of fixed length. And unlike Mac, this hash function or this hash value, it does not use a key to provide the message digest or the hash. And but in case of Mac, we were using a key that was being used for producing the Mac value. And these hash codes, they provide error detection capabilities also. Since the hash code is a function of all bits of the message, when we calculate hash, for example, we have this message and there are some bits 101001110, and out of this message of any length, we calculate the hash value of fixed length. This hash has fixed length, and this is your hash value. It is calculated from the message. So the error detection capability is there because it is a function of all the bits that we are using in the message. Hash code can provide authentication in number of ways. There are different number of ways by which this hash code provides authentication to the message. First one is hash computation, then encryption of the whole message. This is similar to the previous process as we have studied. First, we compute the hash value and then we encrypt the whole message. But here, what is the difference with the Mac calculation of Mac? In the Mac, we were using key, but here we are not using any key. So it is not exactly similar to an encryption function, but it can provide a hash value or a message digest of fixed length. Then second is hash computation and its corresponding encryption. In this first case, we were computing hash and then whole message that is appended with the hash value is encrypted. So first we were computing hash and then that hash is appended to this original message, and then we were doing encryption process here, and after encryption process you are going to get a complete encrypted message along with this appended hash. Okay, so but here in this case at number 2, hash computation and its corresponding encryption. In this case message is here, we are calculating hash value, and then we are encrypting only this hash value. This message is in the original form, and but this hash is in the encrypted form. So encryption is only provided to the hash value here. After that we have hash computation and signing it with the private key. So when we sign any data with a private key, that will provide you the authentication that proves its legitimacy, the legitimacy or the authentication of the data origin. Okay, and then we have hash computation by appending a shared secret value, maybe S, or sometimes it is referred as key K, to the message. So what we are going to do is we are having message and then we are appending some secret value to it, and then we are transmitting. Okay, so this is how the hash codes can provide authentication to the message in the following number of ways. Hash codes not involving encryption of whole message are somewhat preferred because of the following reasons. The first reason is encryption software is relatively slow. Encryption software, if we use more number of encryption processes or encryption functions, that is relatively slow as compared to computing the hash values, hash of the message. So that is the first reason. Although encryption hardware costs are low, we know that hardware costs of the encryption functions are low, but the cost adds up if all the nodes in a network must have this capability. If all the nodes they use the encryption functions in the network, if they use this capability of encrypting the message, the whole message, then the cost is going to be added up in the whole process, and the system is going to be very very slow. So that's why we do not use encryption of the whole message. We just do the encryption of the some part of the message, and that can be your hash value. Encryption hardware is optimized for large data size. When we have large data size, then we need to optimize the encryption hardware. So that is another problem. And the other reason, encryption algorithm may be covered by patents. Sometimes we use the encryption algorithm, but they are the patent. They are the properties of some organizations. So we cannot use them so frequently. They require some cost, maybe in terms of money or some other in other way. So we cannot use frequently such encryption algorithms which are the patents of some organization. So that is another reason why we do not encourage the encryption of whole message. Instead we do the encryption of the hash value, and sometimes we do not prefer the encryption. Next is your requirement of hash function. uh, Hash function can be applied to any size of message, and then we are going to get a fixed length message digest which can be appended to the message and can be transmitted in order to authenticate the message. Hash of x, relatively easy to compute from a given x. As we know that it is a one-way function, and computing hash for a given value x or a given message x, it is easy to compute. And for example, if you have if h is equal to uh, the hash of this x which was given to us, it is computationally infeasible to find x if h is known. We cannot find this x. It is infeasible to find if we know the value of h. If this h is known to us, we cannot find this value of x. Okay, so it is a one-way function, which means that h of x is equal to h. We cannot find that. So for a given block x, it is computationally infeasible to find y is not equal to x such that hy is equal to h of x. Hy is equal to h of x. This is again computationally infeasible because the reason for this is weak collision resistance. So this is all about hash function that we can use as an authenticator to authenticate the message, to authenticate the origin of the data. Next is our entity authentication. Entity authentication allows one entity to prove identity of the other. When we talk about entity authentication, which means to prove the identity of some entity, identity of some entity. And in this case, an entity can be a person. So an entity can be a person, it can be a process, it can be a client, or it can be a server. So entity can be a person, it can be a process, it can be a client, or it can be a server. So here one entity tries to prove the identity of the other, and which gives us the entity authentication. And the entity that needs to be proved is called as claimant. The one who claims to prove its identity in the network, that is called as claimant. And the one who is the proving that particular entry is called as the verifier. This entity authentication, it differs from data origin authentication, which means that this entity authentication, it differs from message authentication in the following respect. The message authentication might not happen in real time, whereas this entity authentication does. So it happens in the real time. So the entity authentication can be done in real time, but message authentication may or may not be done in real time. It may or may not be done in real time. For example, we have for example we take the example of Alice and Bob. Alice sends a message to Bob at the time of authentication of this message the by Bob. Alice may or may not present. When we have Alice here and we have Bob here, Alice sends a message to Bob, and when Bob tries to authenticate this message, Alice may or may not be present at that time. Okay, but if it is a case of proving the identity or the entity authentication of Alice, in that case Alice needs to be online to take part in the entity authentication process. Okay, so data origin authentication is required when an email is sent. So example is email email for data origin authentication or message authentication. Email is sent by the Alice to the Bob, and Alice may stay online or it can go offline after sending the message. But when it is coming from the identifiers of Alice, then the Bob will come to know that it has come from the authentic source. But for the process of entity authentication, Alice needs to be online, and it has to be done in the real time. And the message authentication authenticates one message only, and process needs to be repeated for each new message. When we have message authentication scenario, then for each message we have to prove the origin of the data is authentic. But entity authentication scenario, it authenticates the claimant for the entire duration of the session. For the whole session, that particular entity is authenticated, and then when the session is ended and a new session is started, then the entity authentication has to be done again. That is the difference between entity authentication and message authentication. Then comes verification categories. The claimant identifies himself on the basis of one of the following ways. When Alice has to prove its identity in the network, then Alice can prove its identity by the following ways: knowledge of some secret like passwords, pins, that is personal identification number, and some key. So Alice can use passwords, pins, and keys in order to prove its identity. That is the conventional way. Then position of something that can prove claimant's identity. And in this category, the Alice can prove its identity by producing some identity documents like passports, uh, maybe a credit card, uh, or some I card, identity card issued by some uh, government agency. So these are the ways by which the claimant, or in our case, Alice, can prove its identity. And the third way of proving one's identity is some inherent characteristics of the claimant. Claimant is one who wants to prove its identity, and in that case, you can have an example as conventional signatures of that particular user, fingerprints, handwritten uh, patterns, and facial characteristics. There can be other functions, other parameters by which the Alice or the claimant can prove its identity. Okay, and when we come to these passwords, passwords can be fixed, and passwords can be of dynamic nature. That is what we call them as one-time passwords. When we have fixed passwords, and the fixed password, they are used for every access, and there are various approaches in the scheme. The system keeps a table of the user ID and password, and they are sorted by the user ID, and the user sends the ID and password in the plain text, and the system finds the password from the table by using the ID. And if the password sent by the user matches with the one which is in the table, then access is granted. Otherwise it is denied. And this approach, it is vulnerable to some attacks. The attacks are like eavesdropping attack, stealing a password, accessing a password, and guessing attack. And in eavesdropping, what we know that in this kind of attack, the password although is not shown while it is typed, but it can be eavesdropped by the attacker. So it is sent in the plain text. When we enter the password, we are entering the password in the plain text form, although it is not in the readable form, but it is sent in the plain text form, not in the encrypted form. So the eavesdropping, or the password can be seen by the attacker. So that is what we call as eavesdropping of the password. Then next attack that can be performed on the fixed password is the stealing of the password. So password can be stolen by an attacker if it is written somewhere in your system, or in maybe in your some notebook. And to overcome this attack, user usually remembers the password. But when it comes to remembering the password, then it should be simple, and somehow it should be related to the user. And this makes it vulnerable to other types of attacks, where the user can guess uh, if it is related to some user's name, or some user's residence, or users some ID, or something related to user, then it is easy to steal. Accessing a password file, attacker can hack into the system where you have the password file in the system. And the attacker gets access to the password file. So somehow the attacker gets the access to password file, and then it can take, or it can steal the password from that password file in the system. Then you have another attack, that is the guessing attack. And this attack is more likely if the password is short, or it is related to user, for example his birthday, or the user's child's name, or the some favorite word, or a person of the user. So in that case, the attacker can guess the password. And to prevent the guessing attack, long random passwords are recommended. But then these need to be written somewhere, because we cannot remember the long random passwords. So where we have to write these passwords somewhere, and which makes the password subject to steal when we write it somewhere. So that is also a problem. And then we have the second approach, that is one time password. And in one time password approach, the hash of the password is stored in the file by the system, and the user sent password is then hashed and compared with the entry in the table to grant the access. Since hash is one way function, so the file does not need to be read protected. So as the hash is a one way function, we cannot do the reverse, or the reverse of that function is infeasible. So the file does not need to be read protected. And this approach is vulnerable to dictionary attack. In dictionary attack, we have all the lot of words which can construct our password. So this one time password is susceptible to dictionary attack. And the attacker does the brute force attack, and uses all the words in the dictionary, or all the letters in this. And then it tries to construct that one time password. So it is vulnerable to dictionary attack, and the attacker is interested in finding one of the passwords regardless of ID. So here attacker finds tries to find the password instead of the ID of the user. And for example, if it is a six digit number, so if the the password is a six digit number, then the attacker has to do perform the brute force attack from this number, that is 000000 to 999999. So this is the number space where the attacker has to perform the brute force attack. And the attacker applies hash to each one of the values in this range. And the attacker can get the password file and do offline processing of to find a match. To make this attack difficult, the system uses salting approach. There is a salting approach to make the brute force attack, or the dictionary attack, impossible. and that approach is called as salting approach. In this method, a random string called the salt is appended. So here we have a random string and that is called as salt, and this salt is a random string and it is appended to the password, and the salted password is then hashed. After that, what we do is we take the hash of that salted password and then stored in the file. This increases the complexity of the dictionary attack. For example, a for a 6-digit password and a 4-digit salt, the attacker needs to create a list of 10 raised to the 10 password. If we have 6-digit password and if we have 4-digit salt, then the attacker needs to use 10 raised to power 10 password hashes and do a comparison. So these many comparisons the attacker needs to do. That is going to be a difficult job for the attacker. Okay, so in another approach, two identification techniques are combined. For example, using of ATM, we can use two different techniques like ATM, that is combined with the personal identification number. ATM plus PIN can be used in this one-time password category, and this is also useful in some cases where we need this verification of the user. So this is how the entity authentication is done. There are different ways, and that's all in this lecture. Thank you for watching.